taken by the web. Okay, so to see is this true, right? To see is this true, I'm just going to do it in as an exercise. We are now going to find using force is equal to when we integrate the shear stress multiplied by dA to determine the resistance force by the web. So when that's the case, okay, we know that the limits now change from minus 0.065 y, and it go to 0.015 because the thickness is equal to twice of 0.02 meters, which is equal to 0.04, right? So now we are going to take, if you look at the curve, okay, I'm going to highlight in green, we're going to take the function over here, and we're going to integrate with respect to the limits, right? We're going to integrate with respect to the limits. So we know that we are going to use 32.707 multiplied by 7.741. We're going to use this function now, right? And this function, we have to use this function because the thickness is constant, held constant at 0.04 and not 0.16, okay? So we're going to now integrate 32.707. So F of the web now, okay? So the limits is minus 0.065, okay, 0.015, and then we are going to have 32.707, okay, 32.707 times 10 to the power 6 minus by 7.741 times 10 to the power 9 y squared. And dA, the thickness is held constant at 0.04. And then we're going to do dy over there. Okay, I'm going to copy the exact same function. I'm going to use the next page as I'm running out of page. So I'm going to take this thing over here. Right. So now we just do simple integration. So 32.707 times 10 to the power 6 y minus by 7.741 times 10 to the power 9 y cubed over 3. Limits is 0.015 minus by 0.065, and then we have 0.04 on the outside. Again, I'm going to introduce the 0.04 into that expression over there. So 32.707 power 6 times by 0.04 is 1.308 times 10 to the power 6 y, and then minus 7.741 power 9 divided by 3 times by 0.04 is 103.213 times 10 to the power 6 y cubed, and we're going to operate in the limits of 0.015 to minus 0.065, the lower limit. Okay, so this in turn will be equal to 1.308 power 6 times by 0.015 minus 103.213 power 6 times by 0.015 power 3 is equal to 19.272 times 10 to the power 3. And then minus 1.308 power 6 times by, now you have to include the minus 0.065. And then minus 103.213 power 6 times by minus 0.065 power 3, which is equal to minus 56.675 times 10 to the power 3. So 19.272 plus 56.675 is equal to 75.947 times 10 to the power 3 Newton. Okay. If we just minus off, the value is 75.968. Okay. So we have another value is 75.968 times 10 to the power 3 Newton. They are almost the same. They are not the same. When this is different, slightly different, I think because we have some rounding error. Okay, we round off to 3 significant or 3 decimal places. That's where the issue comes from. Okay. Right. So as you can see, why I'm doing this is you can see that deriving the function of the distributed of the shear stress equation, it's not just okay, I derive it, so what? Okay, sometimes you want to know, okay, I want to know how much load the flange is, how much force the flange is taking, and how much force the web is taking. Okay. Now by saying that, the most important is still stress. Okay, because what induce or how structure fail is due to the stress rather than just the force. Okay, in structure analysis is not is based on a stress function, not based on the force alone. Okay, so the next question that I'm going to do, okay, before I do the next question, there's a concept that I want to drive deep to you all. Is we know that the shear stress, right? The shear stress is equal to VQ over IT, right? We know that the shear stress is equal to VQ over IT. And knowing that V over I are what? Are constant, right? You look at the example that we just done, V over I is always constant. V over I is always constant. V over I is always constant. So therefore, the shear stress is what? Dependent on the what? Q over T, right? So i.e., the higher the Q over T, okay, the larger is the what? Is the shearing stress. Okay. So the first moment of area and the thickness are always fighting one another. Yes or no? Right? If you have a so the Q and T are always are always competing in the ratio. Okay, in the ratio. And I want you to know this concept as soon as possible because this is important. Okay, and that's where the next example comes in. Okay, so this is more of optimization, is the Q over T ratio. Okay, the Q over T ratio, the higher the Q over T, means it can carry is not it has a higher stress. If the Q over T is low, means it is what? Lower stress. Okay. So now let's look at one of the example. Yeah, I think I posted it on yeah, this one. Okay. So let's look at this example over here. So this was a term test question I gave probably about 2 or 3 years ago now. Okay. And let's look at the structure. And this question is based on COVID time, okay, where things were online. Okay. So for a beam having a cross section shown in figure 2, determine the largest value of P such that the shearing stress is not to exceed 1A0 megapascal. So I'm going to change the A. Okay, so this value over here, I'm going to change to 130 megapascal. Okay. So the next part is the wall thickness of the beam such that the maximum shear at the centroid and the region with the smallest wall thickness are equal. Okay. So we are going to, part B is the optimization. So the optimization states that what is the wall thickness of the beam such that the maximum shear stress at the centroid, so this is at the centroid, and the region with the smallest wall thickness, so this is the region with the smallest wall thickness, okay, are equal. Okay, so the outer perimeter, right, of the cross section of the beam must remain the same. So what this means that this region over here, the one I'll change the color. The outer perimeter, this perimeter over here, this size must remain constant. Okay, we are going to change T, right? But the thickness or the outer perimeter cannot change. Okay, so that is the purpose. Okay. So I'm going to put some numbers over here. Okay, so this is 590. And then this is 550. Now, what are all these A, B, C means? Okay, so A, B, C are the last 3 digits of your student number. So this is during COVID time where everything is online. Okay, if you don't change things like that, everyone can copy by sharing information. With this case, it's difficult to know who shares the same student number. Okay, that was the purpose. Right. So by looking at this, right, before we do anything, we have to do some analysis first. Okay, analysis. Okay, analysis. So the thing we ask ourselves is where does tau max occur? Okay, where does tau max occur? Right?